All right, we're going to talk today, number one, about damped harmonic oscillators. And then after we get through damped harmonic oscillators, we'll look at the wave equation a little bit. So a harmonic oscillator, we've already learned about simple harmonic oscillation. A harmonic oscillator is something that's undergoing simple harmonic oscillation. So you have a mass hanging from a spring, that's a harmonic oscillator. The damping is something that takes away energy. And so we have dampers on things, like this door has a damper. So I let the door close and this damper is absorbing energy. So it doesn't just swing shut, it has also spring in it. Your car is the same thing. Your car has springs that mount the wheels to the car. So that when you go over a bump, your car does this. The idea is when you go over a bump, your wheel goes like this, and you don't want the person in the car to go, right? So we have the spring, so when you go over the bump, the tire goes down, but the inertia of the car keeps it pretty stationary. Problem is, your car can do this if you just have that spring. Nobody wants to be driving down the road bouncing in. Well, most people don't want to be driving around down the road bouncing in their car. So what do we do in a car? What do we put in the car to make this not happen? We put in shocks, which is just short for shock absorbers. And the shock absorber is at its essence what we have here. In physics, I think we call it a damping pot. You have, for a shock absorber, two pieces, one that slides inside the other. And then you have a cylinder in there that has some holes in it. And you have a fluid. And so when you hit a bump, the tire drops, and you have the fluid going through those holes that's going to restrict how quickly things can move. And it's going to take away energy. And so this here is just a simple form of that. We just have a circle that moves up and down the water. And the water is, of course, going to apply a force to oppose its motion. So we're going to learn the physics of how this motion operates, which when you think about it, is really cool how we're going to, we can actually do that with our basic understanding. So first, we're going to consider the undamped case. That was not a highlighter. That's the highlighter. The undamped case. So for the undamped case, we just get rid of this stuff here. Gone. And I'm going to start by applying Newton's second law. We're way past Newton's second law, but let's remember to practice. Notice that x is defined as down is the positive direction. So I'm going to make my sum of my forces in the downward direction, Newton's second law. So what do I get when I apply Newton's second law to this little bob?
Minus kx.
Okay, minus kx. Why is it minus?
Because it's a force going in the negative direction.
Yep. What else?
Gravity. Plus gravity.
Yep. Plus because it's going down. I'm glad both of you remember that we're keeping down as positive. It's part of the process of using Newton's second law, remembering what direction is positive. Those are the only forces for the undamped oscillator. And according to Newton's second law, what should that equal? What is it? Somebody slap him for me. It obviously is that, but Newton's second law says sum of the forces equals
In a certain direction.
sum of the forces is mass times acceleration. As I'm sitting here making you feel uncomfortable, let me remind you, only one out of the four of you has done the teacher or course evaluation yet. Please remember to do that. You may not have been here the day when we did it in class. I don't know. Since you looked at me quizzically when I said that.
No, I thought I did it. But I don't know. Mine are all screwed up anyway, so.
Okay. Well, that would be weird if you thought you did it.
I got my emails in like an odd way. Like it was supposed to get them all at once, and I got them like days apart. So I don't know why.
I didn't know that you got emails. I thought that it was just me giving you the link. I hate that.
Well,
what's the point of us taking time in class to do it if they're just going to send you an email?
I think though because some people like me will do it early, and I know that sometimes like in the past they've accepted really specific days, and if a teacher doesn't do it that day, it actually locks you out from submitting it at all. I know I filled ones out, and it's like, oh, the time for this is expired. Like this is the time they allotted. So it's like
perfect.
Yeah.
Well, okay. Moving on. Some of the forces is mass time acceleration. Now this is a calculus class, and this is calculus material. Unlike the calculus that you three are doing right now, we haven't done calculus in what, 3 weeks?
Yeah, at least. We don't do calculus and calculus. It's just made up.
I'm surprised. I mean, they're following the textbook. It's not like you're going off and doing something else, but they haven't done calculus in 3 weeks.
We'll do calculus.
Oh, are you? Okay. What in this equation would make you think calculus? Or to put another way, why did Newton invent calculus?
Well, maybe that you change distance.
The acceleration.
The acceleration.
It's not always constant.
Yeah.
Acceleration is equal to the second derivative of position with respect to time. And so I can write this equation as what we call a differential equation, and I'm going to move everything over to this side. So I'm going to have 0 equals, actually, I take that back. I am only going to move stuff that has x in it to this side. So I'm going to have mg is equal to m d second x dt squared, I forgot to write that the first time, plus kx. This is a second order linear differential equation. Second order because the highest derivative is the second derivative. Linear because each term has x to the 1 power or a constant. It would be, non-linear if it was like x d second x d t squared or plus kx squared. That would be nonlinear. So second order linear differential equation. These are, when you get to differential equations class, you'll say, whew, because they're the easiest ones to do. But you know what? You're not in differential equations class yet. You may have done this, but I'm not expecting you to be able to do it.
So why is it, can you explain the reason for the squares that?
Well, second derivatives.
Oh, sorry.
Yeah, so it's second derivative there. That's what makes this hard. If it was a first derivative, you would just separate variables and integrate, right? That's something you can do already. But with the second derivative, it's a step further. So here's the work we just did. That's the equation we just had, except for I divided everything by m. So this equation here was an intermediate equation. This is where we ended, except for I've divided everything by m. Why did I do that? I did it because one of the things we like to do in differential equations is take the highest derivative and make it so it's multiplied by 1. Just like when you have a quadratic, we always try to make it so you have the quadratic equation, x equals negative b plus or minus square root of b squared minus 4ac all over 2a. We always try to make it so that a is 1. It just makes it easier because you divide by 2 instead of over 2 times something. Same thing here. So that's why it's divided by m. Now there are 2 solutions you get from this. I say 2 because there are 2 types of solutions. As you'll see, there's a total of 3 solutions. The 2 types of solutions, one is called the particular solution. The particular solution is the solution that gives you the answer, the constant there. Or if that was a function of time, that would be part of the particular solution. The homogeneous solution is the other solution. The homogeneous solution is the solution that gives you 0. And you might say, but 0 is not what that's equal to. But the thing is, your answer could be the particular solution plus any homogeneous solution because it's not going to add to the answer. So we have to find the two solutions, the particular solution and the homogeneous solution. And we'll start with the particular solution because that's the one that you actually can do. So for the particular solution, we're solving this equation and we say, okay, we have this as equal to a constant. Now, if the second derivative plus the function times something is equal to a constant, if the second derivative is, let's say, a polynomial, well, let's say x is a polynomial, like x is equal to t to the 5th power. I take the second derivative, I'm going to have something with x to the 3rd power. And I would have to have an x to the 3rd power in my, or a time, time to the 3rd power. And I have to have time to the 3rd power then in my original equation. And it gets really convoluted. And the only one that's actually going to be contributing to the constant is a constant for x. So the particular solution here is particularly easy. You say, okay, for this to work out, I have to have a constant for x. So I just say, okay, if x is constant, then this is equal to 0, right? The derivative constant is 0. And I have x particular is gm over k. So that's my particular solution. For my total solution, it's going to be homogeneous solution plus particular solution. Remember in class I talked about the vertical spring and how it's a little more complicated but behaves the same. This particular solution would have been 0 if it was horizontal. That's the difference. So with our calculus, it's kind of easy to see that, right? If it was horizontal, we wouldn't have had the mg term, right? And thus it would be equal to 0. Nathan?
It seems like it would be, when you solve for xp, still the k would be on top.
Okay, so what I have is k over m xp equals g. So I have to divide both sides by k over m. So those cancel. And then, of course, dividing by fractions, you invert and multiply. All right. So now let's go to the homogeneous solution. I don't expect you to solve this, right? You haven't had differential equations. So what I do is I give you the solution for a second order linear differential equation has the form of x equals e to the ct, where c is some constant. So what we do is we put that constant in, or that solution in to find what the actual homogeneous solution is. So we have the form and we plug it in. Question, Michael?
We plug that equation on the bottom to where?
Not the bottom one, the one in the middle that says x sub h equals e to the ct.
We plug it in for x sub h.
In the equation on top.
In the equation on top. Okay.
So we're going to do this, right? We're not just going to say it can happen. We're going to do it. C is a constant, yes. That's actually why we use C.
I just didn't know what it came from. So.
Yeah. And it's a constant that we're going to find when we plug it in. So I have to find the second derivative. So let's just do the first derivative first. So what's the derivative of e to the ct with respect to time? Exponentials are relatively easy. We want the derivative of this here with respect to time. C is a constant.
So it would be
C to the E to the CT.
CE to the CT. you bring down the derivative of the exponent, and then it's the original e to the whatever. In fact, it's kind of fun to write this as cx sub h. It's kind of fun to write that because I want to find the second derivative.
C squared.
Yeah, it's going to be c squared e to the ct, or c squared x sub h. Right? If you can do the first derivative, you can do the second derivative, right? It's the same derivative. So now we can plug that in. So my differential equation becomes c squared x sub h plus k over m x sub h equals 0. Now, all of us want to right away, well, let me ask what you want to do. It's mathematically wrong, but we all want to do it, including me. Right? I'm not just saying you. What do you want to do to solve this for x sub h?
Isolate x of h.
Okay, isolate x of h. How would you do that?
You have to.
Actually, I'm sorry. We want to solve it for c, not for x of h.
Oh.
Well, c squared.
Well, yeah, c squared and square root. So how would you solve it for c squared?
You have to just subtract k over h, right? X of h. First of all.
Okay, we had two different answers. One was the one I was looking for. One was a step associated with that. So you're both thinking the same direction. The thing that we want to do is divide by x of h. The problem is x of h is sometimes 0, and you can't divide by 0. So this is a technicality that we do just to make sure we don't break our rules. We factor out the x of h instead of dividing by x of h. Now, there are two situations that are going to make this equation true. Either x of h equals 0, or, okay, if x of h is equal to 0, we call that the trivial solution. We've just found the solution of, yeah, nothing happens. Well, we weren't looking for the nothing happens solution. We know that's one of the possibilities, so it's trivial. The other solution is if c squared plus k over m equals 0. And so we focus on that one. So in that case, what is c equal to? Square root of a negative value. When I was a young buck, like 4th grade, my teacher said, you can't do that. You guys remember that? You will find in life that the things you were told in math you can't do, you can do. You just have to do them in a tricky way.
Can't wait
And
till
so-
I divide by 0. It's like, can't wait till I can divide by 0. Make all this math easy.
Good man. So what did we learn to do with the square root of a negative value when we got to higher levels of math?
Just move the name outside.
You can't bring the negative outside, but we say the square root of a negative 1 is I. And yeah, we call it an imaginary number. And for anyone who's not well versed in math, that seems like we've already gone way around the bend. Now, the reason I said you learn the things they say you can't do, you can do, you just have to do it in a trickier way. In particle physics, we have things where you start with something like this, and then you get something more complicated you can't solve. Well, let's try making it a matrix and see if we can solve it with a matrix. And you go through, making a bigger matrix and a matrix of matrices. And, hey, you can do it. And I'm like, who comes up with this stuff? They're pure geniuses. But this one here is within our realm. So now we have the value of c, and now we have our complete x homogeneous, except for one thing. I forgot one thing. I made a mistake. Does anybody know what mistake I made? You probably wouldn't recognize it as a mistake unless you're thinking technically. But it's an important thing.
You mean with this one?
Of HX.
With this, in this box right here, there is a mistake.
Is I supposed to be inside?
No, the i's outside.
Plus or minus?
Plus or minus. Anytime you square root, you have a plus or minus. We often omit that. In physics class, we're doing something, we're solving for time. We don't worry about the negative because there's no sense to how long after you throw the ball does it hit the ground? -2 seconds. I think not. Right? We just ignore it because it doesn't make physical sense. But mathematically, we need to. And so in this case, we have no realistic reason to throw it out, so we have that, which means that we actually had 2 solutions. So we have x homogeneous plus is equal to e to the I square root k over mt, and x homogeneous minus is equal to e to the minus I square root k over mt. I am not going to write square root k over m anymore. We abbreviate things. We introduce a constant. Let omega equal square root k over m. So this is e to the I omega t, and this is I omega t. Well, that's easier, right? Definitely. So we have 2 solutions. And then the bottom line, our actual homogeneous solution is a linear combination of those 2, where the constants capital A and capital B just depend on how you start the system. You start the system differently, A and B are going to be different values. But the omega is going to be the same. And of course, I put C plus and C minus more conventionally. Now, how many people are familiar with e to the I omega t? With only 4, I can monitor all of you, and I saw no responses. Well, we are going to become familiar with that. We're going to learn about Euler. Y'all know about Euler?
Yeah. His name is spelled completely wrong.
His name is spelled completely wrong. The guy just doesn't know how to spell a name. Okay, so we've gone through this already. Euler's formula. We have a couple different definitions for sine and cosine. You guys in calculus class, I'm sorry, Caitlin, you get ignored all the time. You guys in calculus have learned to do things like Taylor series and Maclaurin series, right? And so we can do a Taylor expansion, or Taylor's about 0, right? I can never remember which one's about 0 and which one's not. That's the only difference in Maclaurin and the Taylor series. So we can do a Taylor series for cosine and get one of our equations for cosine, an infinite series. We can also take the definition that comes here from Euler's relation. E to the I theta is equal to cosine theta plus I sine theta. You ever seen that? It's true. Another way of defining cosine theta is equal to e to the I theta plus e to the minus I theta over 2. And sine theta, is e to the I theta minus e to the minus I theta all over 2I. So those are additional definitions for sine and cosine. And you're probably thinking, and here I thought sine was opposite over hypotenuse. That is a very limited case. That's only if you have a right triangle. These are general formulae. So how is that going to help us? Well, let's look at our solution. If I have a I omega 0t plus b e, a e to the I omega t plus b e minus I omega t, I can combine those using Euler's relation. Now, You'll notice I had subscripts of 0 in my work. I didn't write this up here. I should have. That's the resonant frequency if there's no damping. That's why I should have done it. If there's no damping, there is only one frequency to worry about. But because we're going to do damped, I should worry about it. So that's X homogeneous. And now I'm going to use that Euler's formula. Okay, so there I use Euler's formula. What can you tell me about cosine of minus omega 0t? This would go back to last year in your first days of trigonometry class. You all in that, right? How does cosine of negative theta relate to cosine of positive theta? When I worked with Nathan last year, I said that cosine is telling you about the horizontal part. And so it's symmetric whether you go up or down for the horizontal component. So cosine of minus omega t is exactly equal to cosine of plus omega t. And so I can rewrite this as plus b cosine of omega 0t. And then what about sine? How does sine of minus theta relate to sine of positive theta? It's the vertical part, yes. And so how does, if I start here and I go down, how does that relate to if I go up the same angle? The vertical part is?
So the positive, if you put in a positive value, it's going to be negative.
Okay. I think he's on the track there. The sine of minus theta is equal to minus sine of plus theta. Is that what you said?
I think so.
So now if I take these, notice I have cosine omega 0t has a plus b. And sine has I a minus b. So there's another way of writing my X homogeneous. Now what were A and B? A and B were just constants that depend on how I start the system. Well, A plus B and I a minus b are also just constants. Now remember, sine and cosine, those are real functions. Whereas the exponential to an imaginary power is complex. So this is actually nicer because we have now everything's real. So we have a plus b has to be a real constant, and I times a minus b has to be a real constant. We could find new constants. We just like to say, let's just replace this with equals c cosine of omega 0t plus d sine of omega 0t, where that stuff is d and that stuff is c. So we just have two new constants that depend on how you started the system. And these two new constants are dependent on the old ones. You can translate back and forth if you actually care. Why do I want to write it like this? Because now we see, hey, this is sinusoidal behavior. A final way that I could write this is you can combine a sine and a cosine to give you a sine of the same angle plus a phase shift. I'm not showing this technically, I don't feel like taking the time, but you have a sinusoidal oscillation. Remember, we said from the outset in the general physics class that simple harmonic motion requires that you have a restoring force that's linearly proportional to the displacement. And if you have simple harmonic, that condition, you're going to get sinusoidal oscillation. Well, now we've shown mathematically, hey, look, we do. If we have that linear force function that's a restoring force, we will get this sinusoidal motion. Now, I spent a lot longer than I intended on this derivation, but that's the derivation. I used F here instead of G, and I used cosine instead of sine, assuming. It just changes what your phase angle is to use cosine instead of sine. Any questions about our derivation of undamped harmonic motion? Are we all pretty down with that? Does it make sense to you? Okay, Michael?
A little bit, but I just want to have a question on the manipulation formula.
The what?
Like, how, like, is it, like, what is it used for specifically? Like, example. It's for,
What is, well, this formula that we got in the end here,
yes.
by the way, we would have X is equal to X particular plus X homogeneous is equal to, what was it, G M over K. Is that right? We would use this because this allows us to determine what the displacement is going to be at any time. So we have something oscillating and we can determine, okay, it's going to be here, it's going to be here, it's going to be here. Now, in real life, you're actually a lot more concerned with what's the frequency than we are what time is it going to be at its peak. But that's the purpose. That was your question, right? All right, so let's move on to the damped case. We're going to introduce the easiest possible damping case, which is the damping case that occurs if you have something traveling slowly through a fluid. If it's fast, it's going to be proportional to V squared. Remember, we talked about the difference in the drag and the Stokes law fluid resistances. So this is for the case for something moving relatively slowly through a fluid. We have a drag force that's minus BV. So now I'm going to rewrite Newton's second law. So what's Newton's second law? Equals?
MG. Well, in this case,
Okay, it's going to be minus KX minus BV plus MG. And sum of the forces is always equal to MA. All right, so we nailed that. Just like before, I'm going to rearrange this. I'm going to divide everything by M and move everything that has an X to one side and the term that doesn't have an X to the other. Now, remember, A is the second derivative of X with respect to time, so it has an X. What else has an X that doesn't explicitly show an X here? Okay, the V. So I'm going to now use the notation we use in physics class for calculus to make life easier. A dot over it means a derivative with respect to time. So X dot means dx dt, which is what V is. X double dot is d second x dt squared. So if I rearrange this, dividing everything by M, I'll have X double dot plus B over M X dot plus K over mx equals G.
And the purpose of dividing by m is just to make the formula look easier.
It's just to make a 1 multiplied by x double dot. That's right. That's exactly the purpose. All right. Looks good to me. How do we solve this baby? How do we solve this second order linear differential equation? It's once again second order because its highest derivative is the second derivative. It's linear because each one has a single x or no x. What do you think? Now, you're not differential equations expert, so I'm asking what you think. I'm not saying you have to know the answer. Anyone have an idea?
Would we take a common factor out? Like, would we isolate a certain factor out of all these if they were?
No.
No.
Well, we're going to do exactly what we did before. We have two types of solution. We have the particular and the homogeneous. And right away, you can see that it's again going to have the x particular is equal to gm over k. The x particular didn't change. Here's the equation with using dt squared. So the particular solution is going to be the same thing. And the homogeneous solution has the same form. And so I'm going to plug in the derivatives we already did. So I'm going to have c squared x sub h plus cb over m x sub h plus k over m x sub h equals 0. I substituted, we already did those derivatives of x sub h, right? Because it's the same x sub h for the second order linear differential equation. The c can be different, of course, but it's the same form. What should I do now to solve for c?
We take out the x of h.
Okay, we factor out the x of h. So we're going to have which gives us the trivial solution. What's the trivial solution? X sub h equals 0. We just ignore that. What's the other solution going to be? Right? Isn't it nice that we set the coefficient for x double dot to 1 so that our coefficient of c squared turned out to be 1, so we're just dividing by 2 in the quadratic. Because we had a quadratic relation, that thing in parentheses, c squared plus cb over m plus k over m equals 0. To solve for c, we have to use that quadratic. How many solutions do I have? I have 2 unless b over m squared minus 4k over m equals 0. That's a special case. So we have 3 regimes for this solution. And each one actually has to have 2 solutions. Because it's a second order, it has to have 2. And so that one that I just mentioned, the special case, is going to have a special solution. So we take these 3 and we call them overdamped, critically damped, and underdamped. Let me go on to the next slide because it'll be easier than me writing it down. We first are going to define alpha as b over 2m. And we call that the neper frequency, or the attenuation. The reason we call it the attenuation is because when we put e to the ct, That's going to be equal to e to the minus alpha t, e to the plus or minus square root alpha squared minus omega 0 squared t. This term here is an exponential decay. That's why we call alpha the attenuation sometimes. So this term here is going to make my solution go towards 0 as time progresses. This one here, I tried to change color. This one here, it depends on what that square root is. If the thing under the square root is a positive value, then that's again going to be either something that blows up or something that goes to 0. But what if the thing under the square root is a negative value? What do we have then? Square root of a negative value gives you I. And when we have e to the it, that's going to give us the sinusoidal behavior. So we're going to have sinusoidal behavior if alpha squared minus omega naught squared is negative. So we have 3 regimes. Regime number 1 we call underdamped. Underdamped is when alpha is less than omega 0. In that case, that's going to be equal to I times square root of right. I notice what I did here is I reversed the order of which one's positive, which one's negative under the square root and brought the I out. So now I have a real thing for the square root and I brought out the I. So we call this thing right here my resonant frequency. If I have damping, if it's underdamped fits exactly to what you would think. That is if it's lightly damped, so it doesn't have much resistance to motion. Then it's still going to oscillate. But the frequency it oscillates is now this omega resonance, omega sub r, which is different than omega sub 0, which was the natural frequency. And if you look at this, it's omega naught squared minus alpha squared, so it's going to be a smaller value. So it's going to resonate at a lower frequency when you have damping than it would have if it was undamped. So the oscillations are going to be longer period. So if we plot what this is going to look like for underdamped, notice using Euler's formula again, this is just written as 3 pieces, a constant for how big the amplitude is when you start, a phase angle to tell you in what phase you're starting. If you're starting like at 0 with a high speed, or if you're starting at maximum displacement with 0 speed, that's where phi is going to come in to tell you. And then we have the resonant frequency and the attenuation. So we can draw the graph by drawing the attenuation. The blue here is showing the exponential decay for attenuation. And then we put the sinusoid inside. Now there is a little idiosyncrasy to this. If you are really careful, which is virtually impossible to be, you find that the point where your sinusoid is touching the envelope of the attenuation is at the highest point of your sinusoid function, but not at the highest point that your total function reaches because of the attenuation. So it's a little bit off, but we won't worry about that for our level of class. The important thing is you now have an oscillation that is dying out. This is what you want in your car's shock absorbers. You want that shock absorber, you push down on a fender, you let go, and it should come up and it should bounce maybe 3 times and stop. If it keeps going more than 3 times, your shock absorber is bad. Now, if you have something like, plush Cadillac, you press down the fender, what happens? It just goes shh.
Oh.
Those things are damped differently to give you a different ride that's, a smoother, less handling ride. I think that's right. So this is underdamped. Overdamped is when you have it, so you have just a huge amount of resistance. If you have a huge amount of resistance, then you're going to have, we just say, let beta be that square root of alpha squared minus omega naught squared. And so we have e to the minus alpha plus beta, e to the minus alpha minus beta, or if you prefer, e to the minus alpha t times ae to the beta t plus be to the minus beta t. Once again, a and b are parameters depending on how you started it. And your motion for this overdamped is going to have some crazy motion like this. It's not going to oscillate. Now, if it's overdamped, it's not going to cross the 0 point, right? It doesn't have any oscillation ability. It might go up because if you start it that way and then come back down, but it very slowly gets to equilibrium. Overdamped is going to take a long time to get to equilibrium. So if I have this door overdamped, I push it open and let go, and it's going to really slowly close. This didn't close super slowly. Also, if it's overdamped, it's not going to slam when it closes. It's just going to go and stop. So this is not overdamped because it came and you heard it hit, right? Not overdamped. So then we have the last one, critical damping. Critical damping has this special equation, and we're not in differential equations. We're not going to come to how we get that. But you have the same attenuation, but then you have a polynomial, a plus bt. And so when you have critical damping, it may do one loop, or it may just come down and approach 0. It depends on how you start it. Critical damping is going to reach 0 the quickest. But it's also going to come in gently on 0. So for something like this door, we don't do critical damping either because we don't want it to just come gently in. We want it to come and latch. So the door is slightly underdamped. Slightly underdamped, it's going to reach 0 faster. It's still going to be moving, so it'll latch. So in practical applications, we have cases where we want to use underdamped, cases where we want to use overdamped, and there are cases where you want to use critical damping.
What would be a case of something you want to be critically damped?
I can't come up with any off the top of my head. I'm sorry. It's a good question. I'm sure there's plenty of them. I'm quite sure, but I can't come up with anything off the top of my head. All right, we are out of time, so we will not go to the wave equation. We will stop here. I'll see you for lab today. Don't forget to do the lab pre-lab quiz. Check and make